All right, so we're continuing talking about capacitors here. The two main equations that we've talked about, well, we've talked about a few, but for capacitors in general, we know the capacitance is equal to the ratio of charge per potential difference, delta V. This, of course, can be written, we will often see it as Q is equal to C delta V, or we could also solve for delta V, which would be Q over C. But the three are always related. Now, Q and delta V don't determine C. They don't determine the value of the capacitance. But the value of the capacitance is directly related to Q and delta V this way. We've also talked about a capacitor storing energy, so the potential energy stored in a charged capacitor. One way to write it is 1/2 C delta V squared. I'm putting subscript of C's on our delta V as well as the energy, U, so that we're distinguishing these equations are specific to a capacitor. Nothing else, a capacitor. In a circuit, when we connect a battery, so I'm just going to draw my battery here for a second, like it's a little AA battery. This end of the battery is the positive terminal, the bottom is the negative terminal. A battery is a source of potential difference. So between the positive end and the bottom end, there is some sort of delta V, assuming it's a good battery, of course. We are going to assume ideal batteries, meaning the chemical reactions inside theoretically last forever. Realistically, of course, that's not the case. But we are going to assume that the chemical reactions will last forever. This battery will give us the same potential difference forever. Okay. We use another symbol. We can totally call it a delta V for the battery. But we also end up seeing, for ideal batteries specifically, delta V of a battery, we also will see this as what looks like an epsilon. That's not the constant, epsilon naught. This is called, in abbreviated form, EMF. What that stands for is electromotive force. This was the terminology in Benjamin Franklin's time that they came up with because they recognized there was something that was making charges move. And so that's the term, electromotive, charges moving, force. So something was exerting a force of some sort, causing charges to move, and that was what they decided to call it. It became abbreviated as EMF, and we now often use it to represent an ideal battery. And so we will sometimes see battery voltages written as a delta V. Sometimes we will see them written as this epsilon looking figure. Okay. When I take a battery, I'm going to label this epsilon. I don't know that it's technically epsilon, it just looks like it. So that's what I'm going to call it right now. A capacitor in a circuit we draw as if it were a parallel plate capacitor. Okay, so we connect a battery to a capacitor. The capacitor is not just instantaneously charged. It takes a little bit of time, not a whole lot. But because the wires connecting to the electrodes of the capacitor as well as the electrode itself and the terminal of the battery, are all conductors. So as a reminder, right now we're going to assume electrostatic equilibrium has been reached in any problem we look at in this specific chapter. So if we see only capacitors, that's what we're going to assume. Why is because we remember that inside a capacitor, electric field is 0, delta V then is 0, meaning V final equals V initial. That means for any 2 points on or in our conductor, they're going to have the same electric potential value. So if I look at this positive terminal of my battery and the wire that it's connected to and the plate of the capacitor it's connected to, all of this, I'm going to call it V sub plus. All of this ends up at the same positive potential. Everything conductively connected. Similarly, the negative terminal of the battery, the wire connected to it, and the wire connected to this bottom plate of the capacitor, that is all conductively connected. So in this equilibrium state, everywhere here will have the same negative potential. The difference in potential, the delta V, for this specific capacitor, having just one capacitor, is equal to that V positive minus V negative, just in terms of magnitude. But V positive is the same as the positive terminal of the battery. V negative is the negative terminal of the battery. In the case where we have one single capacitor attached to our battery, and we're talking specifically equilibrium has been reached, the capacitor's voltage difference or potential difference between its plates will be the same as the battery's potential difference. This is always going to be true for one capacitor attached to a battery and that's in equilibrium. This electrostatic equilibrium that we've been talking about. Now, getting to this point is not an instantaneous thing. It does take a little bit of time, which we will talk about that in a couple chapters. Right now, what we need to know is that capacitor, its potential difference between the plates will be the same as the battery. If I come back to my equations, this single capacitor, we could easily solve for the charge then that accumulates on either plate. The higher potential plate ends up with a positive net charge. The bottom, lower potential plate ends up with a negative net charge. In our equations up here, Q means just the magnitude of the charge on either plate. Well, that Q is C times delta V, but we now know delta V is equal to the battery voltage if we have only one capacitor attached to the battery. Awesome. Energy. The energy of this capacitor, meaning stored by the capacitor, if we plug in the battery's voltage, would end up being 1/2 C, that epsilon, battery voltage squared. These equations up here the top three are the same equation, just isolating for the different variables. Energy and this capacitance is charge over delta V. These are valid for any one capacitor at a time. I can use it for capacitor 1 and a capacitor 2 and a capacitor 3. That's fine. But they relate to that specific capacitor I'm talking about. So this, what we just looked at, is a single capacitor connected to a battery. Okay. We sometimes need more than one capacitor. And there's two fundamental ways we can connect these capacitors together. So let's walk through that. One way that we can connect capacitors is called in series. What we mean by series is that if we were to follow a path from one end of our battery, if we were to set up multiple capacitors, we would take a wire from the positive terminal, connect it to one plate of a capacitor, and then we would take another wire from the other plate of that capacitor and connect it to the plate of another capacitor. And then we would take another wire and connect it to another capacitor. And theoretically, we could keep doing that for as long as we needed or wanted. And eventually, the last capacitor we attach, we would take a wire from its other plate and connect it back to the battery. So still using the symbol for the ideal battery. If we think about that equilibrium state, so that V positive I drew before, that's still going to be true. The positive terminal of my battery, this equilibrium means the wire also ends up with the same positive potential as well as the top plate that that wire connects to. Those all end up at the same potential. Similarly, the negative terminal of the battery connected to the wire, connected to this bottom plate, because we're talking equilibrium, we end up with all of this with the same negative electric potential. So ultimately, we have between here and here that represents the battery voltage. But that also encompasses three capacitors. So what we can say is that battery voltage is somehow shared between those three capacitors. If I had drawn 4 capacitors, I would say plus a delta V4. However many capacitors I have in series, those have to be added up to, in the case of the battery here, add up to the battery's voltage. Okay. So by delta V1, I mean the potential difference across capacitor 1. By delta V2, I mean the potential difference across capacitor 2. By delta V3, I mean the potential difference across capacitor 3. Okay, let's talk about charge for just a second. Let me grab a different color here for a minute. Let's go with purple. In order for this bottom plate to end up with a specific potential, it ends up with a negative charge. That very top plate at that positive potential will have a positive charge. But if we think about the charge, Q, the negative net charge on that plate induces a positive charge on its companion plate that makes up capacitor 3. essentially, the negative charge down here is repelling electrons from the other plate, leaving it positively charged with the exact amount of charge, but positive. Well, if the electrons were repelled, they moved through the wire, but they could not go any farther than this bottom plate of capacitor 2. That's as far as they could get away. Well, that means this is the same Q here as down here. And in turn, this other plate of C2 will end up with a positive charge. The electrons that were repelled are now on the bottom plate of C1, which in turn means the positive charges on C1 are the same amount. This is something specific to capacitors in series. In series, all capacitors have the same charge. So I'm not calling them Q1, Q2, Q3. They're just all Q, the same thing. All right. Using our relationship for capacitors, if Q is equal to C delta V, then the potential difference across a capacitor is Q over C. If I come to this relationship for electric potential, I'll talk about the left side in just a second, but delta V1, using this relationship, would be the charge on that capacitor 1 divided by capacitor 1's capacitance. Similarly, delta V2 would be the charge on that capacitor divided by its capacitance. Delta V3 would be the charge on it divided by its capacitance. Now, EMF, remember, was valid for a single capacitor, meaning if this circuit was a battery connected to only one capacitor, we could say delta V of this capacitor would be the EMF of the battery. So I can say the EMF of the battery would be the charge on this single capacitor divided by whatever its capacitance is. We call this an equivalent capacitance. Ultimately, instead of having 3 capacitors in series, could I have just bought one with a different value of capacitance that would end up storing the same amount of energy that the 3 in series did? That's what we mean by equivalent. These 3 capacitors in series are the same as if we had simply put one capacitor in. I'm going to put Q over C equivalent up here. Well, in series, they have the same charge, and they have the same charge as their equivalent capacitance. That's a Q. Meaning, if I knew the battery voltage here and an equivalent capacitance, I could find the Q on this capacitor because it's a single capacitor, so Q would have to equal C times the battery voltage, the EMF. But this Q is the Q that each individual capacitor would have when we really have the 3 specifically in series. That's why I can cancel Q out here, and that leaves me with a relationship that says 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. If I had more capacitors in series, I would just continue adding 1 over C4 plus 1 over C5 plus, and just keep going for however many I had in series. Okay. If we know the values of C1, C2, and C3, then we can ultimately come up with an equivalent capacitance. So let's just make up a circuit with some of those, with values of a capacitor. Okay. Side note, batteries, we often see them drawn as two straight lines, but not equal length straight lines. Our battery will be a long line and a short line. Or you may even see it as a long, short, long, short. That's fine as well. The long line always represents the high potential end of our battery. The short line always represents the low potential end of our battery. C1, C2, C3. So let's go ahead and make up some values. Let's say we have a 12-volt battery, and we've connected it to 3 capacitors. Let's say we have 10 microfarads, our next one 20 microfarads, and the next one 30. Why not? What I would like to do is find the charge and potential difference for each capacitor individually. So, for example, for C1, I want to find a Q1 and a delta V1. And then capacitor 2, a Q2 and a delta V2. Okay. All I can say right now is these 3 capacitors are connected in series. In my opinion, the easiest way to recognize that quickly is to just follow a path from one end of the battery through the circuit, keep going, keep going, keep going until you eventually get to the other end of the battery. If that path requires you to pass each capacitor, then they're in series. That means they have to have the same charge as each other. Each capacitor has to have the same charge, and they have the same charge as their equivalent. In series, as we just saw, 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Okay. So in this specific problem, we can say 1 over C equivalent is 1 over 10 microfarads plus 1 over 20 microfarads plus 1 over 30 microfarads. Now, I can totally plug this into my calculator, or I could go ahead and find a common denominator. Either way is fine. Oops. Sometimes a common denominator works out nicely, sometimes it does not. Let's go ahead, though, and find a common denominator for this one, just as an FYI. So a common denominator would be what? 60. So we would have 6 over 60 for this first. 60, we would get 3. 60, we would get 2. 6, 7, 8, 9, 10, 11. Okay, but please keep in mind that this is equal to 1 over C equivalent, meaning we need to flip it. C equivalent will be 60 microfarads over 11, which does not turn out to be a nice, beautiful round number. I end up getting 5.4545 continuing across my calculator screen, so I'll just take it out a couple of those. The units on these are going to be microfarads because that's the units on C1, C2, and C3. What this tells me is this original circuit that I drew will be as if I had a 12-volt battery connected to one capacitor that has a value of this 5.4545 continuing microfarads. One reason we would not potentially just choose this one C equivalent at the store is because they probably don't sell this value. You can go to, like, I don't know, Radio Shack is what comes to mind. I have no idea if that's even actually valid or if that store even exists. You can buy capacitors, but you can buy certain values of capacitors. So sometimes you might need to combine capacitors together to get an overall capacitance in your circuit that you need. All right. In terms of answering this specific question, though, what I need to do now is find Q on this equivalent capacitor. Because I know if I have an equivalent capacitor a single capacitor, then the delta V for my single capacitor is equal to the battery voltage. And that's 12 volts. So now that I know what those three capacitors are equivalent to, I can multiply them by this 12 volts, and this will tell me how much charge would accumulate on the plates of this capacitor if I only had this one capacitor. Oh dear. Sorry, I pushed the wrong button. Okay, so I'm getting 65.454545. I'm going to keep a few decimal places. Technically, let's just keep the 4. The 4 sig figs. I still have my micro because I did not put 10 to the negative 6 in my calculator. If a coulomb per volt is a farad, then a farad times a volt is a coulomb. So this charge right here is the charge that accumulates on the plates of this one capacitor. But it also represents the charge that had to move to accumulate on the plates up here in our 3 capacitors in series. That's why each of these capacitors have the same charge as their equivalent. So we can essentially say Q1 equals Q2, but it also equals Q3, which is this value of 65 microcoulombs. I'm going to round to 2 sig figs because that's what it gave us to start the problem as far as answering this part of the question. The charge on these 3 capacitors individually will be 65 microcoulombs. Okay, we want delta V now. Well, we're going to use our nifty equation, Q equals C delta V, again, but this time we're going to solve for delta V. we know delta V is equal to Q over C. So delta V1 will be the charge 1. We know how much charge is on here, and I am going to keep more digits until I get my answer here. So charge divided by the capacitance of C1. So delta V1 is Q1 over C1. So let's see, delta V1 ends up being 6.5 volts. I'm going to write that at the bottom just so we can see it better. So I'm using a less rounded version of Q in this calculation just to minimize rounding errors. But I am rounding my delta V because this is one of my answers. Delta V2 would be Q2 over C2. Same equation, but values for capacitor 2. Well, capacitor 2 has the same amount of charge, but it has a different capacitance. Notice I didn't mention it before. The micro part cancels because both of them are in terms of micro. Here, when I'm getting 3.27, but my answer should only be in 2 sig figs, so I will write it as 3.3. Well, finally, delta V3 for our third capacitor. Same equation, Q over C, but specifically the charge on capacitor 3 divided by the capacitance of capacitor 3. So same charge, different capacitance. The micros cancel out again. I'm getting 2.181818. So to 2 sig figs, I would write this as 2.2 volts. So here are the potential differences for across each capacitor. So for each capacitor, the delta V between the positive and negative plates for the two capacitors, for each capacitor, sorry. Notice if I add these together, they add up to be 12 volts, which is the battery voltage. Which needs to happen. In series, we add up all of those potential differences and they will equal the battery voltage. That's specific to series itself. Okay, so just a reminder, series means if you follow the path, so coming back to our original picture, if I start at one end of the battery and just follow a path around my circuit as if I could walk it and get back to the other end, series means I have to pass by each and every capacitor. That's what we mean. One comes right after the other, which comes right after the other. There's no other path to take where I would pass by one but not the other. That's specific to series. Okay. I'll make another video for our next connection, and that's parallel.